So far in this lecture, the focus has been on the quantity of radiation. How do trees respond to low levels of radiation or high levels of radiation? How do they adjust to those? But in addition to quantity of radiation, the quality of radiation also impacts growth, development, and physiology of trees and other plants. And when we're talking about light quality, really what we mean is the wavelength of light. Now, wavelength, at least within the visible spectrum, also means color. When we perceive colors, we're perceiving different wavelengths of light. And the approximate zone of light wavelengths that humans can see is from 400 to 700 nanometers. So wavelengths from 400 to 700 nanometers. So that's basically going, from the purple and blue wavelengths into the red. So down here at really short wavelengths, we're dealing with UV, ultraviolet wavelengths, for instance. Out here into the long wave, so UV. Out here into long wave, we're talking about far red is sort of the wavelengths right beyond red, and infrared. Okay. When we're talking about sensing of light quality and responses to light quality, we're primarily talking about sensing that's going on in sort of this zone in the red and far red wavelengths. Now, the most important linkage for sensing light quality in trees and other plants is phytochrome. Phytochrome is a photosensitive chemical that acts as a multi-purpose sensor of wavelengths of light. And the way it works is by basically having two forms that interconvert, that change back and forth depending on the quantity of red and far red wavelengths that strike them. So there's a red phytochrome form that absorbs light in the wavelengths of 620 to 680 nanometers. So that's red light. And then the far red version of phytochrome that basically absorbs radiation in the range of 730 nanometers, which is far red. So when the far red version absorbs light in that wavelength, it converts in this direction and converts to the red form. When the red form absorbs red light, it converts in this direction to the far red form. So those are, for instance, given equal quantities of red and far red radiation striking that photoreceptor, there's basically equilibrium between the two forms of phytochrome. But if the balance between red and far red radiation shifts, that then in turn shifts the balance between the red phytochrome and the far red phytochrome. And that shift in balance triggers physiological responses. So I'm going to talk about several examples in which phytochrome, through sensing balance between red and far red, the presence of light, or the reversion of far red back to red forms, all of those interconversions acting in different ways enable phytochrome to act as a sensor of light and light quality. So one example of phytochrome is sensing competition. So I'm going to tell a story that started out with a counterintuitive observation. And this was in a planting density trial. One of the more important applied questions in forest management is how close together should you plant trees when you're establishing a planted even age stand? If you plant the trees too closely together, they will compete with each other and you won't get large individual trees that are suitable for harvest. If you plant the trees too far apart, individual trees will become large, but the site will not be fully occupied and your amount of wood produced per hectare, for instance, will not be as great. So finding the appropriate density for planting to provide desired outcomes in terms of wood, for instance, is an important applied question. So it's not unusual for foresters to plant density trials. So this is an example of a density trial where trees were planted at planting densities ranging from about 200 trees per hectare up to 3,000 trees per hectare. And this shows some data measured relatively early in that trial, probably at 1 or 2 years, maybe 3 years, showing DBH, diameter at breast height, and height of trees across increasing planting densities. And what you're seeing, this is all relative to the highest planting density. What you're seeing is that as density increases, individual tree size is also increased. So as the trees are planted closer together, individual tree diameter and height gets larger. Mean diameter and height gets larger. This is a counterintuitive result because, like I mentioned before, when we plant at wider densities, we tend to expect, so when we plant at lower planting densities, wider apart, we tend to expect bigger average tree size. So this was puzzling. And this was in a Weyerhaeuser trial in using Douglas fir. And this was actually back in the day when Weyerhaeuser had a number of tree physiologists working on staff. Weyerhaeuser was huge and almost had a university worth of scientists in it. They've streamlined since then and there are fewer scientists there. But at any rate, a scientist named Gary Ritchie, a physiologist named Gary Ritchie, said, let's take a look at this and figure out what's going on. So what Gary Ritchie did was plant some seedlings in a Nelder plot. Nelder plots are density tests that are planted in an arrangement like this, where trees are planted sort of close together in the middle of the arrangement and get further and further apart as you go further out into the arrangement. So you basically have trees growing at less dense environments and more dense environments across a gradient. People plant these types of density trials with full-size trees. So this is an example of a Nelder plot in loblolly pine in southern Brazil. I'm in the middle of the Nelder plot looking up at the most dense part of the Nelder plot, and as you move out into the outer parts of the Nelder plot, it gets less dense. So it's just a method of testing density. Well, Gary Ritchie took potted seedlings of Douglas fir and arranged them in a Nelder plot. He called it a Nelder fan here. So he had seedlings growing in a situation where they are far apart from other seedlings and very close to other seedlings. So he's showing here basically his measured trees, and he expressed his data relative to plant area. So what was the area around each plant? So the smaller the plant area, the closer the spacing, the tighter the planting density. Now note, these are in pots, so these trees are not competing with each other underground. They're in well-watered pots with plenty of fertilizer. So we're really looking at any above ground interactions among these seedlings. So what Ritchie found was that in trees planted or growing close to each other, so remember this is growing area, so over here is more dense. This is less dense over here. So trees further from each other. And trees closer to each other. That as those trees were, as you went across that gradient and trees were growing closer to each other, they tended to allocate more biomass towards shoot growth. So that root to shoot ratio that he's expressing there shows that as you get more dense, or as the seedlings are growing closer to each other, they allocate less to root and more to shoot, so that ratio goes down. So what this is showing is that trees growing closer to each other shift their allocation towards the shoot. So that's a proximal physiological explanation for why in that field trial that they measured diameter and height, those trees growing closer together were on average larger. They were likely shifting their allocation towards above ground growth at the expense of root growth. And what Ritchie did was, across that same gradient, again, this is less dense and more dense, he measured the red to far red ratio at each of those locations. So this is the ratio of red light to far red light. So in the open, so sunlight basically, red to the far red is maybe 1.1 to 1.3. Okay, so there's a little more red than far red. But as those trees were growing closer together, the red to far red ratio went down. Okay, so I've already told you that there's a mechanism for trees to sense the ratio of red to, or the amount of red light and the amount of far red light. So what we are seeing here is likely a physiological response triggered by the change in red to far red ratio encountered by trees that are growing close together versus trees that are growing far apart. But why does the red to far red ratio vary depending on how close a neighbor is? Well, this is how it works. When trees are growing far apart, so this situation on the right, for instance, a low planting density, trees planted far apart, that any particular tree is mainly getting light that's coming from the atmosphere. So they're seeing that red to far red of maybe 1.1. But when trees are growing closer to each other, they're seeing more and more radiation that's been reflected off of adjacent plants. So for instance, this tree, some of the radiation it's encountering has been reflected from adjacent plants. So what? Well, keep in mind what wavelengths of light are absorbed by chlorophyll, red and blue. So leaves tend to absorb red wavelengths. So radiation that's reflected from a neighbor will tend to be depleted in red wavelengths. So this reflected wavelength will have red to far red less than 1.1, less than that above the canopy. Okay, so trees or plants growing in close proximity to each other encounter or are in an environment with a decreased red to far red ratio. So think about it, trees or plants growing close to each other are competing with each other. So there's a potential adaptive advantage to having a sensor that can sense neighbors. And that altered red to far red ratio is essentially a sensor of competition. And in young Douglas fir, the response to that competition is to grow more rapidly above ground. Okay, the end of that story is that this is a relatively short, transient response of Douglas fir. If once you followed out that spacing trial as those trees got older, the results end up looking like we would normally expect, with trees growing closer together being smaller on average than trees growing far apart. But that initial, essentially seedling response is an initial response to competition that likely imparts an advantage by increasing above ground growth to essentially outgrow competitors. And this has been observed in other plants as well, and not even in non-woody plants. They see this response to competitors growing close by. So phytochrome can be a sensor of competition and trigger physiological responses which cause increased growth in response to competition. Phytochrome can also serve as a sensor of overstory. Or the composition of the overstory. And that's because the red to far red ratio underneath broadleaf canopies tends to be different than underneath conifer canopies. So for instance, like I mentioned, red to far red ratio in the atmosphere from the sun tends to be about 1.1 to 1.5. Under broadleaf canopies, red to far red ratio is much lower, 0.08 to about 0.28, whereas underneath conifer canopies, it's much higher, about 0.6 to 1. That's because broadleaf canopies, those leaves tend to be thinner and allow more transmission of radiation through the leaf blade, whereas conifer needles tend to be opaque. They do not transmit light. So a lot of the light in the understory of a broadleaf canopy has passed through leaves and therefore been depleted in red wavelengths because they're absorbed in those leaves. Whereas in a conifer canopy, much of the light in the understory has passed in between needles because the needles don't transmit much radiation through them. And so that means there's not as much depletion of red wavelengths underneath the conifer canopy. So what is the significance of that? Seeds. This is some data from a study looking at germination of alder seeds. So they had an experiment where they placed alder seeds in Petri dishes, and they wrapped some Petri dishes in aluminum foil, so they were in complete darkness. So this is just aluminum foil. And then they placed those dishes in a clear cut out in the open, underneath a Douglas fir stand, and then underneath an alder stand. And then in another set of Petri dishes, they were uncovered, or at least covered with glass. And they placed those in the clear cut underneath a Douglas fir stand and underneath an alder stand. So a couple of things. First, in complete darkness, mean germination was very low. Okay, there was a little bit higher germination in the clear cut, but not by much, still very low germination. That's likely an effect of temperature. Temperature likely stimulated germination of those alder seeds. But overall, very low germination. So basically, in the dark, alder seeds don't germinate. But when uncovered, there was very high germination of alder seeds in the open and underneath the fir stand. So very high germination. And much lower underneath alder. This is good evidence that alder seeds have phytochrome that enables them to sense the red to far red ratio. Well, actually, it allows them to sense two things. One, that phytochrome can sense the presence of light or the absence. But also, as we know, phytochrome in seeds senses red to far red. Because like we said, the red to far red underneath a conifer canopy like Douglas fir is similar to the red to far red in the open, like in the clear cut. Whereas in the alder stand, the red to far red ratio is lower. So alder seeds have phytochrome, and the responses essentially slows or prevents the germination of alder seeds when they're underneath alder. That's likely an adaptation that then allows alder seeds to remain in the seed bank, but then to germinate after a disturbance when the canopy is opened up. It's just that there's no ability to detect the difference between that opening and a fir stand because the red to far red ratio is similar. So a really neat example of the use of phytochrome in seeds to sense the red to far red ratio and whether there's light or not, and to use that as a trigger for breaking of seed dormancy. Yet another function of phytochrome is to act as a daylength sensor. And I put daylength in quotes because in reality it's actually a night length sensor. I say that because this function occurs because of this dark reversion pathway. So let's say a tree or a plant is in the light and there's some balance between red and far red phytochrome. And then the sun goes down and it's in the dark. So there's an equilibrium of some sort between red and far red. But in the dark, the far red starts reverting slowly back to the red form. That happens relatively slowly, but over time, sufficient far red reverts to red to trigger physiological responses. So in other words, if the night is long enough far red will convert to red to trigger night length physiological responses. Experimentalists determined that it was actually the length of the night and not the length of the day that was triggering these responses by basically in the middle of the night flashing for just a few seconds or maybe a minute white light on the plants. And when they do that, that basically disrupts this pathway and resets the equilibrium between the red and the far red. And when that happens, you don't get the long night length response. So by breaking up that night length, they determine, it's actually the length of the night that determines those day length responses. But we still often call those day length or photoperiod responses. So there's lots of phenological responses that are associated with this sensing of day length or night length. So for instance, shoot elongation, cessation, or bud set. That is often determined by the shortening of days. Leaf abscission, so leaf drop. Is often triggered by shorter days. Some frost hardening mechanisms, so physiological preparation of plants for cold weather, is often triggered, at least partially, by lengthening nights. Bud break, so the starting of growth in the spring is sometimes partially associated with shortening night lengths. Flowering in some plants, but not in trees generally. So generally forest trees are relatively day length insensitive with regard to the timing of flowering. The final point I want to make with regard to this is that most responses of phenology to day length are conditioned by other environmental signals. So, for instance, the breaking of bud in the spring is probably partially determined by shortening nights, but it also is usually triggered by some accumulation of cold nights. And probably the same thing with frost hardening. Frost hardening is partially triggered by lengthening nights, but is also triggered in combination with changing temperature regimes. So there are a few responses that are solely day length triggered. Partially because, keep in mind, the same day length or the same night length occurs 2 times a year. So usually there has to be some other set of environmental signals that in combination with that night length cause that physiological response. So it's important to keep that in mind. So for instance, this is an example of flowering. I have a Christmas cactus on my front porch. And if I just leave it out on the front porch, it doesn't flower until New Year's Day or Valentine's Day. Well, it's a Christmas cactus, but because of the day length, night length patterns in Florida, we don't encounter long enough nights by Christmas to trigger flowering in the Christmas cactus. So if I remember in time, like around Halloween, to take that plant inside and put it in a closet where it encounters really long periods of dark, maybe for a few weeks, that then will trigger flowering, and I can set it out on the porch after Thanksgiving, and it will flower during the holidays. So that's an example where night length is really important for triggering flowering in that Christmas cactus, but not in most forest trees. There's lots of variation among species. So this is a table, a review of species according to whether bud burst in the spring is sensitive or insensitive to photoperiod, so night length. Some species are photoperiod sensitive, some species are insensitive, some we're not sure yet. So there's lots of variation among species in sensitivity to night length. But so take home message, Phytochrome, super important for conditioning responses to light quality. So Phytochrome can be a sensor of competition. Phytochrome can be a sensor for a seed as to whether it's under a canopy or in the open or in the dark or not. And phytochrome can serve as a sensor of night length or day length or photoperiod. So really important concept and photoreceptor with regard to responses to light quality.